Hello and welcome to Numeristical. We are now in the 13th video of our series on baseball prediction. So in the last video, we were able to take the model we built to predict the number of runs scored by a particular team, put that together, take the model with those two teams together to come up with a probability on the number of runs scored, probability distribution on the total number of runs scored, and then use that to evaluate whether the probability that we would be over or under or a push, given the particular line, over under line set by Las Vegas on that particular game. And we showed some pretty promising results. We showed that it seemed there was pretty good evidence that we were doing better than 50-50 and actually, in fact, doing well enough to potentially make some money. But we wanted to have a little bit stronger evidence. So in this notebook today, what we're going to do is we're going to go through the same analysis, but we're going to have a bigger test set. And this will give us more games on which to evaluate our model to give us a stronger sense of whether we actually do have an edge or whether or not we just got lucky. And after we do that, we're also going to do some further simulations to get a sense of, suppose we do have the edge that we think we have, how much money would you expect to make betting using this strategy? And what's the probability you might actually even lose money, even if you did truly have an edge? And I think those are really interesting questions, and I think this will be really illuminating. So before we go forward, again, if you could please like this video and subscribe to the channel, helps me out a whole lot. And again, just want to remind you, I do have a private Discord channel. If you'd like to join, I will have an invite to that in the description. It will only be good for 7 days though, so if you're watching this video far after the fact, that link might not work. Ping me and I'll see what I can do. And with that said, let's get into the notebook. Okay, so in this notebook, we're really going to repeat the same evaluation we did before, but we're going to do it on a bigger test set, and we're going to see, whether this gives us a little bit more evidence, a little bit more confidence that we actually have a model that can predict the over/under with enough edge to beat Las Vegas. And then we're going to say, okay, let's assume we have this edge that we think we have. How much money would we expect to make? Could we still be losing money? What should we expect to happen if we played out this strategy? So this notebook starts out, it's really the same thing as the last notebook. Do the imports, load in the data. Again, we're going to use 16 as our truncated maximum. So 16 here means 16 or more. So when we try to predict our probability distributions, we'll be predicting, was it 0 runs, 1 run, 2 runs, and so forth, up to 16 or more runs. And here's the part we're modifying. So we're now making our training set a little smaller. The training set's only going to go up to 2017, and we're going to use 2018 as our validation set for early stopping. And then we're going to let our test set be from 2019 through 2022. So we'll have 4 seasons. 2020, of course, was a shortened season, but we'll have 4 seasons of data on which to evaluate our model to see, can we actually predict this over/under with enough of an edge to make some money. So all of this is the same feature set. We're building these individual models. I've already run the corsage model. Again, everything's the same here, except just with a slightly smaller training set. We're going to have a slightly bigger test set. And now if you look at the log loss, this is the value we get. Hard to know really what to make of that without any context. But again, we can look at some of the distributions we get out of this model. And again, you see they have different shapes. Sometimes they max at 2, sometimes they max at 3. But this shows us what's actually coming out of our model. And again, all this is the same. We've got the same function here. We're going to go through our same analysis. I'm not going to go through this again. This is all in the last video. One thing I will point out is we now have 16,358 games, so we have a lot more games than we had before. we still have this effect where the under was a little bit more likely than the over, about 48 to 46.8, so maybe not a huge difference anymore. But our model certainly seems to favor the under, which is interesting. And again, I don't quite know what to make of that, but you know, we will see how it fares in practice. But our model certainly favors the under a lot more. Here are distributions. Again, they're roughly look the same as before. Here's the probability on the over. And again, we have a smaller tail to the right. So the right means more likely. So these over here are games where the over is very likely. And here's the games where the under is very likely. And you see if you start kind of at 0.6, you see this shoulder here, 0.6, much bigger on the under than it is on the over. Again, not quite sure why that is. Here's what the pushes look like. And we're going to use our same function that we said that where you can put in how much of an edge would we need to bet, and then what would have happened if we went through that whole test set. So let's see now. So now you see if we put a threshold of 0.25, we would have had 160 games now to bet on in our test set. And we would have been correct 86 of them and lost on 66 of them and 8 pushes. And so we would have made about 0.08 per bet. So for example, if you bet $100, that would mean you'd make on average $8.37 per bet, and your total profit of 13.4. Again, 13.4 measured in bets. If we go to threshold of 0.2, we've now got 197 wins versus 147 losses. The rest pushes. Whoops. If we go to lower the threshold again, here we get, just to reiterate, we get a total profit of 35.3 here, so that's getting to be pretty significant. We lower the threshold more. Again, we're still more right than we're wrong, but the edge starts dropping down and we actually make less of a profit. And same thing as we go to 0.1. Now, again, we're still more right than wrong, but not enough to beat the Vegas edge. And if you go to 0.05, again, now you're really losing a lot of money. You barely, you're right a little bit more than you're wrong, but not enough to beat the edge. So now let's look at these likelihood ratios. And we talked about this last time. We're a little function that just says, given the number right, the number wrong, we're going to sort of discard the pushes. We're going to evaluate what's the likelihood of that observation under a null probability and under an alternative probability. And the idea being, typically we'll put the null probability at 0.5, assume that our model has no predictive power. What would be the likelihood of seeing the data, and then we'll put some alternative probability. And last time we kind of said we'll just use we'll do what they might call empirical Bayes, where you say I'm going to pick my alternative probability to be what my observed probability was, and we'll play with these assumptions a little bit to sort of test ourselves. And again, this is not meant to be super conclusive or anything like that. It's just meant to give us some confidence, like give us some sense of, how unlikely would we be to see this under if we really had no edge whatsoever. So this is for threshold 0.25, and again, our likelihood ratio 86 versus 66. So again, there's a big edge here, but it's a small sample size, so the likelihood ratio is not quite so big. Now when we do this next one, we see a really big likelihood ratio. So this was for the threshold 0.2, so let me scroll down so we can see that. This was threshold 0.2, and you see that this was the one that gave us the highest total profit across our betting of the thresholds that we looked at. So this is saying that to see data this extreme, so this is pretty extreme, 197 wins versus 147 losses. This is quite unlikely to happen. This is a big enough thing that it would be pretty unlikely to happen if we were just flipping coins. If we were to flip this many coins, 197 plus 147, it would be really unlikely to get 197 heads versus 147 tails. And it would be much more likely to see that data if this was their true probability. Now again, this probability is a little bit cherry-picked because I'm picking sort of the best possible probability. But this likelihood ratio of 38 is pretty compelling to say it's 38 times more likely to happen with this probability than to happen with a 50-50 coin. So this has started to make me feel a lot more confident that we are actually onto something. Now if you go through, now when we start bringing the threshold down, our edge starts getting smaller. So it's still 6, it's still reasonable. If this was bigger than anything we saw in the last, when we used the smaller data set, we didn't even get as high as 6. I think the biggest we had was like about 4.5. So this gets to 6, and if we use a smaller one, okay, now we're already down to like 2.5. So now we're getting into the, yeah, we probably have a little bit of an edge, but it's hard to tell. But this number is very convincing to me. But to be kind of extra sure, I want to poke on this number a little bit. So I'm going to poke on this a couple different ways. Now, we saw, if we scroll back up here, that the under was sort of more common than the over anyway. So let's say somehow you knew that there was this bias built in, and you said, you know what, I'm just going to bet the under every time. I know that the under is a little better, so I'm just going to bet the under every time. And so if you did that, you would expect to be right with this probability. Again, we're discarding the pushes. So this is the probability of under divided by the probability of under plus probability of over. So let's just look at what that number is. So it's 50.7%. So again, to try to poke at this 38 ratio and say, okay, maybe I have a couple of favorable assumptions in this number. What if I made this a little bit less favorable? So the first way I'm going to make this less favorable is, rather than using 0.5, since we could get 0.507, 50.7%, just by betting, by a very simple rule of just betting the under every time. Let's see what my likelihood ratio would be if I replaced the 0.5 with this 0.507. And you see it drops down to 19, so it does drop down, but it's still, 19 is a pretty convincing number. 19 is, roughly equivalent to like a p-value of 0.05. So this suggests to me that even if you kind of bake in a favorable assumption, we still have pretty convincing evidence that we have an edge. And now I want to do a second thing, which is to say, okay, the other thing going on is that we're picking the alternative probability to be like the maximizing probability, to be the exact right probability. So this is saying, what's the probability we have, exactly the edge that we demonstrate in the data versus the default one. So what if I said, okay, how much more likely would it be? I'm not going to pick the best possible number. I'm going to go halfway between the default probability and this sort of like perfect number. And I'll call that the mid-prob. So I take the default probability, I take our previous alternative probability, and I find the midpoint. I'm going to call this mid-prob. And now say, what's more likely? This default, how much more likely is this mid-probability, which isn't sort of the best possible, most likely probability for this data set. How much more likely is this mid-probability than this new default probability? So I'm, again, sort of trying to cut down this likelihood ratio a little bit. So this mid-probability is only about 54% versus this, let me just show 197 divided by 197 plus 147 is 57%. So in our data, we had about a 57.2% edge. But now let's say, okay, suppose I'm comparing, do I have a 54% edge? Maybe I have a 54% edge, maybe I only have a 50.7% edge. Which would make that data more likely, and by how much? And we still have this uh, this 54% probability is 9 times more likely than this 50.7% probability. So again, I'm just trying to sort of do some robustness checks and test it and say, do we still have a pretty big likelihood ratio, even when we're not favoring things as perfectly in favor of our model? And what we're saying is that this just means like, hey, this kind of holds up. I mean, we've made this much less favorable, and it still holds up with a 9 likelihood ratio, which is still pretty good. And there's other general evidence. I mean, we're above 50% at all of these thresholds in choosing the correct, in being correct versus incorrect in what is putatively a 50-50 bet. So, this starts giving me a lot more confidence that we're onto something. Now, there's still a bunch of caveats here, so let's talk through those. But before we go through those caveats, let's now simulate the future and see like how good is this. So let's say let's imagine we're right. We could be right 57.2% of the time. This 197 over 47, we could achieve this in the long run over a lot of bets. And our model will pick these out for us. It's going to do just as well on future test sets as it did on this test set. So how much could we expect to make betting? Let's say we use this strategy for an entire season. How much money would we expect to make? Well, we got to do a few things here. So first, let's look how many games are there per season. So you see, other than the 2020 season, there's 2,430 scheduled games. If you take 162 times 30 divided by 2, that's what you get. So there's 2,430 games in a season. Of course, some games don't get played. They're rain delay games that they don't make up because they don't affect the outcome of the season. But if we look at our model for that threshold that we thought was pretty good. So for this threshold, we only bet on 362 games. So there are only 362 games that gave us the edge that we needed to make this bet. So the percentage of games that we're betting on is 362 over 16,358. That's how many games were in this test set. So we're only betting about 2.2% of the games do we have enough of an edge to bet on. And so in a season at this threshold, we're only going to bet on like 53, 54 games. Again, assuming the future plays out like the past did. So let's play this out now. Let's say for a season we bet on 53 games. We bet some amount of money. You could just choose what your bet size is. And let's say we're going to be right 57.2% of the time. Let's simulate what would happen over 50,000, hypothetical seasons where we use this betting strategy. And what this is going to tell us is we're going to just use a binomial variable to say how many times did we win. We're going to bet on 53 games and we're going to be right 57.2% of the time. Our wins tell me how many times we won in that particular season. The losses, obviously, is all the other ones. Again, we're ignoring these pushes to simplify the analysis. And then how much money would I win? And remember that we're going to assume that we're betting at this negative 110 line, so that we lose 1.1 bets when we lose. So we lose like $11 when we bet, but we only get $10 when we win. And let's make a histogram say how much money do we win in this season. So you see that on average, we make about, 6-7 bets, something like that, worth of money. But there's still a pretty good chance that we'll lose. So if you look at what's the probability that we would actually lose money, 21% of the time we'll actually lose money. And this is, again, assuming that we're right. We really do have an edge. We are right 57% of the time, but even if you're right 57% of the time, you could get unlucky. You could get unlucky. And how unlucky would you have to be to lose money over 53 games? Not that unlucky. I mean, 21% of the time means it happens. That's more than like, rolling a six on a six-sided die, right? So this is really interesting, I think, because it's really easy to imagine that, you play the strategy and you look at, you bet on your first 20 games and, you lose 12 and you win 8 and you're like, oh my God, like something's totally wrong. I'm totally losing. Or likewise, you could have some strategy that's not particularly good and you win 12 and you lose 8 and you think, hey, I'm up 4 bets. Like I'm clearly rocking here. And the idea is that these are very small edges that we're talking about. And it really takes a lot of data, a lot of observations to really demonstrate that edge with a high degree of certainty. So you have to be very conservative on both sides. Don't read too much into if you win the first, if you're winning after a small sample size or if you're losing after a small sample size, you can't read too much into that because it really could go, really could just be luck on these small sample sizes. Okay, now let's repeat this analysis. Let's say we do this for 5 seasons. So we bet on, I'm going to call it 50 games a season. We're going to bet for 5 seasons. And again, we're right. We've got this 57% edge. How much money are we going to win? So here you see we win more money. On average, we win about 25 bets worth. So if you're betting $100 a game on average, after 5 years, on average, you'd be up $2,500. But there's still a good chance that you'd lose money. Not as big as before, but still 5.4% of the time you'd lose money after 5 years, after 5 seasons of betting. So this is all to show that this is hard. It's still hard to make money, just because I have a pretty good certainty that this model has some validity. Would it be hard to make that much money on it right now? And the other thing is this is the happy path. This is assuming that our model works, that we have the edge that was demonstrated in the previous data, and that it holds up going forward, right? So what are some of the conclusions we can draw from this? One is that the profit is small relative to the amounts bet, right? You have to, again, if you bet 250 games and you win about 25 bets worth. So if you're betting $1,000 a game, that's $25,000. I mean, that's money. That's real money. But that's over 5 years. Again, because it's only a small number of games that we're going to have this edge on. And even with this edge, even if you're right, there's still a reasonable chance that you'll lose money. So these are things you have to think about if you're actually going to try to make money off of this. Now the good news is this was really our first stab at a model, right? I picked I just took the feature set we had before. I didn't do any iteration of feature selection. There are lots of ways we can improve. So we might be able to pump up this edge and also get an edge so that we have a significant enough edge on more games, right? That's what we really need to improve, is that we want to have more than 50 games a season to bet on. We want to have a much higher number of games that we feel confident that we have an edge on. The bad news, though, is that this model could be off going forward, right? So the biggest thing is that there were all these rule changes, right? So we've got the bigger bases, you've got the pitch clock, you've got the infield shift rules, right? So those could affect the model significantly. Like in particular, the infield shift rules might mean like, hey, there's going to be more scoring because before people were using this infield shift, presumably that helped the fielders, hurt the batters. Now there might be more runs scored. Who knows? Is that reflected? Maybe that gets reflected well enough in the features that we have, because everybody's on base percentages will go down. Their slugging percentages presumably would go down. So that might be reflected, but it's really hard to know how that's going to play out. Okay, so what are our possible next steps? There's a lot to do with this now. So I really, I did the first thing I thought of to get to something that would make reasonable predictions, and we've got some pretty big results, and there are lots of things we could refine, right? So one thing is it'd be nice to explore these run scored model a little more, poke on a little more closely, and um, see how valid it is, see how well calibrated it is. When we say, hey, there's a 10% chance of a shutout, does that prove to be true in practice? When we say there's a 12% chance of scoring exactly 8 runs, does that prove to be true in the long run? So we can look at that, and that might give us some ways to improve our model. It might suggest some avenues for improvement. Second thing is, okay, let's say those run scored models are pretty good by themselves. We still are using this independence assumption, right? And that might cause some problems because of what we discussed. Whereas teams are going to behave differently, make different strategic choices based on the run deficit in the game. And so in particular, what that means is if another team scores a lot of runs, that team that presumably got a big lead or something might make choices that lets the other team score more runs on average because they're just they're not so worried about losing that game. And likewise, in a closer game, it might favor the under more because if the game is tied 2-2, teams are going to be very conservative and just try to score one more run late in the game. So again, hard to understand all these dynamics. It could go totally opposite of what I'm suggesting. But what we can do is rather than just given those two distributions, rather than using this independence assumption to compute those probabilities, we could build features out of those probability distributions and then try to predict the under over that way. So we could say, given that a team has this run scoring profile and the other team has this run scoring profile and the over under is this, let's build a model for over under versus over under or push. Let's actually build that model and see what a gradient boosting model or something like that would what kind of calculation that would make based on data versus based on kind of a simulation from an independence assumption. So that's another direction we could go in. Generally, again, we can improve this run scored model. I haven't really done anything with feature selection or hyperparameter tuning or any of that. The corsage model has lots and lots of hyperparameters that maybe we'll get into as we go forward. But potentially some improvements we had there. What else? We could use the run scored model now to develop features for predicting the winner against the money line. So again, we can now say, okay, this team has this run scored profile, this team has this run scored profile. What's the likelihood of winning the game for either team? Use these as features to go back to that first problem, the money line one, which we didn't have that much success in trying to beat Las Vegas on. See if whether this run scored model would help with that. Another thing we could do now with this run scored model is try to predict the run differential and see if that could help us predict the money. So now that we're paying attention to the specific number of runs scored, it's less common in, well, there's two things. Let me back up for a second. We could try to predict the run differential. So in other words, rather than building a model just on winning or losing, we could build a model and say, what's the differential? Did the team win by 1 run, 2 runs, so forth? Did the home team win by 1, home team win by 2, so forth? Predict that run differential. And then that might, again, help us to predict the winner. And to my last point, that might also help us if we wanted to bet on the spread. So betting on the spread is a little bit less common in baseball. So in football, generally, you bet against the point spread, right? They'll say -6.5 for this team. So if that team wins by 7 points or more, they get the win. If they win by 6.5 points or less, or they lose the game, that counts as a loss. So that's how the most common bet in football. In baseball, you can bet on the spread. It's a little bit less common, but using these run scored models, that might give us some insight into how to bet against the spread. So there's a lot to go forward here. I haven't decided what we're going to do next, but there's a lot of interesting stuff to poke on and explore. So I hope you'll continue to watch. And with that said, I'd like to just ask once again, if you could like this video, subscribe to the channel. It really helps me out. We will have another video coming up soon. I don't know what we're going to do next, but it'll be something fun and interesting, I promise. Have a great day.